Good morning, everyone at DVClub Europe. Greetings from California at O Dark 100. We're here today to talk about, the three vendors who are doing portable stimulus. I will be here to talk about practical application of portable stimulus, specifically cache coherency verification. So I have a fairly short agenda. I have a slide on who Breker is in case the name's not familiar. But the meat of this is, well, who needs to care about cache coherency, especially if we have an audience of SOC verification engineers over here. And then we're going to talk about how one is supposed to verify caches using the transition tables, how a formal guy would approach it, and the kinds of tests that we need to do. And once we have defined a model for how we must do cache coherency verification, we will talk about how we can make it portable. So what this will mean is how can we define the model once and use it at the IP level, subsystem level, full chip? How do we reuse it from simulation to post-silicon? We'll spend a little bit of time talking about how we can debug these tests once we've generated them, and we'll talk about coverage analysis and closure. The overall point over here is that portable stimulus and reuse of test cases at SOC has become a big thing here in the last 6 months with respect to an accelerator committee starting and so on. And there are the simple use cases where we're trying to get one IP to drive another IP, and this is of course necessary. But I invite you to look into doing some slightly more complicated scenarios where we really need to go test corner cases with a lot of opportunities for randomization. About Breker. So Breker was founded in 2003. We have been doing portable stimulus of some form or the other since about 2008. Fair amount of experience in this area. We are driving a good amount of the work on the Accelera Portable Stimulus Working Group. Those of you who are not involved with the group, we definitely invite you to come join us if you have interest in this area. The core technology at Breker is based on graph-based scenario models. So Mentor and Breker are the two companies who said, hey, maybe graphs are a decent way to capture complex scenarios, and I invite you to see how that works over here today. One of the things that Breker did was turn out a cache coherency Trek app. This is basically a prepackaged solution for verifying caches, and this got quite popular for us. Popular things are very good for little companies, and especially with the advent of the ARM v8, the 64-bit architecture, this implied that coherency became a system problem instead of a CPU-level problem, and needed much more verification than was needed before. Okay, cache coherency. This is a processor heads problem, right? Why are we talking about it? We're all SOC verification engineers. And in all fairness, I am an ex-processor head, so this is why I know a little bit about it. But let's go see who actually cares. So we're going to go build some big SOC. We're going to have our cores, we're going to have our fabrics, we're going to have our memory controllers and I/O devices and so on. This is what we do day in and day out. Why do I care about cache coherency? Well, I got to get some kind of a coherent fabric, and I got to get this thing configured, right? Maybe the CCI 400, the CCN 500 series. Arteris has got something coming online. There are a few other member companies who are building coherent fabrics, and we, as SOC developers, are responsible for configuring that thing. And there are many ways to configure it. We hope we got it right, but we would like to test that we got it right. Okay. Once we've got our fabric up, well, I guess we want to get some coherency traffic running across the clusters. Within the cluster, well, maybe our vendor, typically ARM, has given us the cluster as a unit. That thing better work by itself. But now I've got to send traffic across this fabric. Let's make sure that I configured the fabric right. All right, we got memory controllers. They have queues in them. That has implications on memory ordering, which is a very important aspect of cache coherency and how the whole memory subsystem works. We better make sure that works correctly with the weakly ordered memory system in ARMv8 and the barriers and so on. Yes. Our IOs, our IPs now, we want to make them IO coherent. We wish that when they do master a memory transaction, those transactions will in fact snoop the L3s, L2s, and L1s. Okay, coherency getting to be more important. Oh, we want to talk about IP virtualization. This means that not only might we want to mirror multiple copies of registers, but the IPs actually have handles on page tables and the rest of the system. Page tables, huh. This used to be a CPU thing. Why do I, but all of a sudden I have to care about these page tables and their various possible settings because they're going to play in with my IP block. Oh, once you start talking about page tables, there's this ugly thing called DVM, which is a kind of a barrier operation that needs to be propagated through the system every time anything changes in the page tables. So the issue over here is that we've got to make sure that whenever a page table update happens, everybody's TLBs are updated. Got to worry about that. Oh, wait a minute. My architects put in some kind of a fully coherent agent, a cache that is going to work alongside the caches coming from the processors. Okay, well, I guess we better make sure my new cache works well with the rest of the system. Well, that in turn brings in my level 3 cache and or a snoop filter that's now part of the system. Got to make sure everybody's playing well together. The CPU caches, my coherent caches, and my L3 cache. Or you might say, no, Adnan, my design's not that complicated. I let software manage all of my coherency. Software program is responsible for evicting the right code at the right time. Well, that still has implications of ordering. You do these evictions, you've got to push the barrier instructions so that everything makes it to the right place at the right time. So the net of it is, cache coherency used to be something that was limited to the CPU cluster, and we didn't used to care. But now it's affecting almost all of our system, and perhaps one view of our system is we're building a memory subsystem with a bunch of IPs hanging off it, and we're building a coherent memory system with these IPs hanging off it, and there is much work to be done in cache coherency. Okay, maybe we buy that idea, but exactly who in the design flow is supposed to worry about cache coherency? Surely it's only the guy who's building the L2 or the L3 unit bench for the cache. Well, maybe so. But perhaps we can take all of our caches, our L1s, L2s, L3s, our fabrics, our memory controllers, and bring that all into a transactional unit bench, basically testing the entire memory subsystem. And perhaps this is a worthy thing to verify. Well, that's good. What happens when we go to full chip simulation? Oh yeah, okay, now we have the processor in play, the GPU in play, maybe we need to do coherency verification there as well. Now something interesting happens. At the L2 level, at the subsystem level, we're doing transactional UVM style verification. But once you go to a full chip, all of a sudden we need software-driven tests. We need some kind of a C program that's running on our overall system. Oh, but once we're doing SOCs that are quite so big, simulation is rather slow, we need to go to something faster, and maybe we want to go to an emulation platform. Emulation is good. Perhaps some of us do FPGA prototypes of some kind. And then finally, of course, there's the silicon itself. And do any of us dare say that these verification, this cache coherency verification system-wide feature, is there any step over here that we cannot do verification, right? We're going to have to do cache coherency verification at every stage. Okay, so what is this about cache coherency verification? How do you verify caches? So hopefully everybody in this audience went to Computer Architecture 101 and have some notion that caches are fast memories that we put close to our processors to address the so-called von Neumann bottleneck that getting to memory is a slow slow thing with respect to CPUs, so CPUs like to hold on to recently accessed data. There's a whole science around how we verify caches, but the basic concept behind them is that cache lines go through various states, the so-called MESI protocol, right? Modified, exclusive, invalid, and shared. And they can be described using state transition tables that say, okay, if I start in a given state and I get a particular operation coming in from a particular agent, here's the next state I should end up with, and here's what I should see going out of the cache. So this is how most formal guys would describe their entire coherency protocol. What we want to do is to walk these state transition tables to create some multi-agent scenarios. So maybe I want to have core 1 do a load, core 0 do a store to the same address, then maybe have core 1 do a load exclusive, followed by some external VIP doing a store exclusive. This is the typical kind of scenario what we want to do. And we want to interleave many such scenarios into one test so we get many concurrent scenarios. So how can we model this for portable stimulus? So it turns out that the state transition tables, you can map them onto a state machine, right? You have a starting state, some action, a to-state. That to-state gives you another action, gives you another to-state, and so on. And state machines, in turn, can be directly mapped onto graphs. This is a mechanical translation. Once you have this model, you can traverse it n times to get n of these transition scenarios. And now you can schedule that into a concurrent test case. So each of these get interleaved. There's some scheduling of the work to make sure they fit. There's some scheduling of which memory should go on which piece of work. There's some dependencies to resolve, but other than that, you can simply sit there and walk this graph multiple times to create multiple scenarios and populate some concurrent test case. A detail that comes up over here is that, okay, if we are working with one cache, a single L2 or a single L3, this is fine. But what happens when we start getting into bigger subsystems where we have multiple coherency agents? Well, what you end up with is you end up with multiple transition tables to worry about, and that results in multiple interacting state machines. And this means you're going to end up with a decent-sized graph, right? Your model is no longer tiny, it's no longer simple. Actually, it was not really simple when you had one cache, but when you had multiple caches, it's quite big. However, it turns out that not all state combinations in a system are valid, and the overall problem comes out to be fairly tractable. So it's a big problem, but computers can go handle them fine. Okay. Now, doing those transition chains are fine, but really to go properly verify coherency, there's a bunch of other capabilities you've got to worry about. I don't have sufficient time here to give a complete lecture on the details of cache coherency and what needs to be verified, but here's a quick list of the kind of features that need to be crossed together to properly test cache coherency. We've got to worry about those state transitions. We've got to worry about how various processors can share memory. We've got to make sure that we pick addresses that cross cache line boundaries. This causes different data to have to be collected from different parts of the hardware. We've got to worry about the various page table attributes. We've got to do coherency across multiple physical memory types, right? We have a DDR, we have an onboard memory, and so on. There are various processor-specific instructions to worry about. You might do short operations with single instructions. You might want to do blocks of operation where you do a coherency verification on a block of 6K, say. Memory ordering is a very big deal in coherency verification. We might want to interleave some power scaling, make sure that our caches are properly retaining state as we turn off the cores, which is simple, starting to turn off complete clusters, which give us slower power down states. And we want to do both ordered and unordered test cases. So that's the problem we want to solve. Now let's talk about portability. So once we have a test case, now once we have a model a tool can reason about, then vendors can go off, build technology to go do the rest of it for you, right? The whole objective over here is build a model once, use it many times. So one approach, one aspect that we all very much care about is software-driven test generation. So once we have the test scheduled and defined, we can generate some C program that comes through a compiler and runs the system. And then for each test case, perhaps we can also generate some look-aside file that has some additional information about the test. And as this test runs at key points in the test, we can send some event ID to a runtime component, in Breker's case called TrekBox, that can manage the test bench itself. So this gives us some runtime capability that is used for 3 different functions. One, it is used for debug. It gives us some sense of where the test is at. Second, it is used to manage the VIPs, either driving transactions onto them or checking outputs received by the VIPs. There needs to be coordination of the traffic on the VIPs with what's going on in the software-driven test. And third, it gives us a measure of concurrency coverage, and I'll talk to you about that a little bit more when I get to coverage and coverage closure. So that's our software-driven verification, but it turns out that once we have this model, it is general enough to drive to any one of these platforms. So basically, you end up with this model and you build a platform-aware test generator. If we're going to a unit bench, we can drive transactions for it. If we're going to a subsystem bench, we can drive transactions across the entire subsystem bench. Over here, we're showing 8, 9, I don't know, about a dozen odd agents that need to have coordinated traffic going across them. These are very much the kinds of thing that Breker is doing in anger at customer sites today. We, of course, want a software-driven verification for the simulation environment, but then we wanted those tests running in emulation, in prototype, in post-silicon. And the issue over here is we would think simplistically that the same C test should run on all these platforms, but in reality this is a little bit hard to pull off. These platforms have very different constraints and very different capabilities. For example, in simulation you want to make lots of use of backdoor memory accesses, whereas in post-silicon there is no such concept as a backdoor memory access, but we can burn many more CPU cycles to check something. And we want a generator that can generate the right test for the right platform. So this is the concept of portability. Okay, this is all well and good. What about debug? In verification, our first problem is getting very good tests. Our second problem is being able to make sense of what happened when things fail. Well, one way to look at debug of multi-agent test cases is to come up with this idea of a test map view. So perhaps we can have different columns showing what's scheduled on different agents, different processors. Time is running top to bottom over here. Perhaps this can be an interactive view that updates the test is running, where the nodes that are green have already run, the nodes that are yellow flashing are running. We know they started. We have not heard that they finished. The blue nodes are still waiting to run. And we have some indication of which units connect together to form a scenario. So you can see this cache 18, Snoop 5, and cache 17 all play into one scenario. There are many such scenarios interleaved, and we have a good sense of what's happening across the system. So how does this tie back to our cache coherency tests? So once you have a framework like this, you can start looking at the test and seeing what's going on. So maybe I have CPU 1 doing a write to some address, this 1CBC of some value 3262. He's done a write, so now we expect that cache line to be in the modified state. Then I might have some other agent give me a snoop by reading that same address and checking that I got the 3262 value I just wrote. Now maybe I think I am in the own state in CPU1. I'm going to do a read on it and check that I still see the same data. Then I might do a write hit on it and expect to be in the modified state again. So all I'm trying to show you here is I've peeled out one of those multi-agent scenarios within this test case. Picking the right memory addresses in this kind of work is very, very important. So we just picked an address for this scenario that is an 8-byte operation that starts at this 1CBC address. What's important about this address is it straddles a cache line. So at C0, we're going to cross over to the next cache line, and to fetch this one 8-byte read, the hardware might need to go get 2 cache lines that could be in completely different places in the system. One might be in our L1 L1 and the other one might be down in the L3 or in the GPU's cache or something like this. And guess what? Meanwhile, concurrently, we're running a completely different scenario that is so-called false sharing on the same cache line. So he is using some address 1CC4, which is the next address after the one being used by the 8-byte operation. And this means that I have two different agents both trying to access the same cache line. We're not quite sure where it's going to end up, but we know that that cache line is going to be bouncing all around the hardware. This is a good thing for verification, for a coherency verification test. What about debug? Well, we can look at the same picture and be thinking about debug. So let's say something fails. We get some red node that says, okay, on my schedule, here are all the things that ran, and here's the one that failed. Here's your message of what mismatch we got. Here is where in the source code we got the error. And by the way, this can be one view into debug that flows across all levels of reuse, right? It's easy to see that if we're running in simulation, emulation, and post-silicon, all software-driven, this definitely makes sense. If you're running transactional tests, you don't get a C test over here. You get the list of transactions that were sent for this block over here, but nonetheless, the same debug view holds. So what we're doing over here is, as we're starting to create high-level tests with many, many agents, we're coming up with high-level views of the test case itself. Well, high-level views are good, but we're DV engineers. We don't wish to give up our Verdi or whatever waveform viewer is our favorite waveform viewer. Well, we can integrate this view into traditional debug. So what we're showing over here is the test map view, the interactive view, showing you what has failed. You can click on one of these. Perhaps you're running a hardware-software debug platform that will take you to the appropriate line and the appropriate instruction in the software. This is effectively your GDB for verification engineers. You can single step through there until you get to the right point in the code. You can start wandering around in Verdi, looking at your signals. You might realize, oh, no, my problem really happened 2,000 cycles ago, and you move your cursor and all the windows synchronize. So this has provided a very nice way to start with a high-level view of the test and what is unhappy, move down into the hardware-software debug world, and then move down into the waves world, and this is for a software-driven test. If we're doing transactional verification, of course, there's no C code, so you don't have the hardware-software debug part, but you still synchronize the test map view with the waveform view. So that's a little bit on how we can debug with portable stimulus. Now let's talk about coverage analysis and coverage closure, right? Verification is about generating the right tests, generating the right checks, and doing coverage. I've shown you that the stimulus being generated is not only the tests, but also their self-checking test cases. Now let's go look at our coverage. So it turns out that if you were just to go instrument your design and see how much coherency traffic is coming off of your test, you could go run some fairly sophisticated directed test that's geared towards trying to do coherency, and you will get a certain degree of coherency traffic. However, you start running some heavyweight cached coherency app, and all of a sudden you get a lot more traffic running through the system, and we have an inkling that, okay, we don't know what's going on, but a lot is going on. This is at least good, but not good enough. What we really want to know is, hey, have we done all of the scenarios? Have we done all of the transitions that were defined in the state table that we started with? Have we gotten snoops from every possible aggressor to every possible victim, and so on? So it turns out that once you have the model, you can do some kind of coverage analysis of it. In our case, we do graph-based models, so we're measuring which paths to the graph were exercised when we generated the test, and we get some fairly traditional view of coverage from that model. And it turns out that we're able to come up with this information when we generate the test before we even run it. So this is good because you can run a test, you can generate a test, look at the test map, say, yeah, okay, this is the kind of thing I want to run, and yes, I'm kind of seeing this sort of coverage I want to see before I launch into a big batch of simulation. Turns out, though, that's not enough. we want to know that we've done these various transitions, but we also want to have some notion of concurrency and concurrency coverage. We want to know that we've done various things at the same time on our systems. We do lots of concurrency, and things work differently when we do two operations at the same time versus doing them one after another. So perhaps one way to solve that problem is when we generate a test case, we have some view that is the map that was created by the test case and by the generator. But really, this is a scheduling problem, a packing problem. We don't know how long each operation will really take. But after the test is run, perhaps we can get some back annotated view that shows us, okay, how long did each operation really take, and perhaps we can come along and have some analysis to say, okay, how often have I seen my DNA operation, my UART operation start within the 100 cycles of each other, and so on. So this is a very nice way to show that, okay, I'm running big verification on cache coherency. I've done all my transitions. I've sent snoops from every source to every destination. I've done all my eviction cases, and I've seen all my concurrency cases. One very nice thing about graph-based models is that they lend themselves to automatic coverage closure. So this is unfortunately something we have not been able to solve in the industry with algebraic constraints as provided by System Verilog. Companies have tried and failed. But the graph-based coverage turns out to be very tractable. And what this means is if you have some graph-based model and you run randomly, you see very much the same behavior you see with constrained random verification with algebraic constraints. Coverage tends to asymptotically roll off around the 80–85%. But then you throw the coverage closure switch on the same model, and the tool will go figure out what tests it needs to run to make sure it gets 100% coverage. And this is always a very convenient thing. Okay, now that we have all this nice coverage data, we have information about our coherency coverage, we have information about our concurrency coverage. We wish to merge this with the rest of our global coverage information that's coming off of our design. So, of course, we need to be able to export this or unify this information somehow with the rest of our coverage information coming in from simulation, coming in from formal, and so on. So we've got to be able to merge this information. And that's pretty much it, coming in at 27 minutes of half an hour. Okay, so thank you very much. Any questions? I am here to answer them.
Any questions from Bristol? I've got one question, please, Adnan.
Sure.
I mean, can you give us an indication of the size and the number of tests that you would need to generate to verify the type of SOC you showed at the beginning?
Yeah. So it very much depends on where we are in the food chain, right? So where's my picture? So clearly, number of tests we need at the L2 is smaller than the number we need at the subsystem level, which is then smaller at the system level. The discussion of what coverage closure means to us still remains as murky as it did when we had constrained random with algebraic constraints. It is possible to count up how many transitions it takes to cover the entire transition table, and this will give you a few thousand transitions. But then there are many ways that those transitions can interact, so you're doing long chains of these transitions. So it ends up being we can create a lower bound of, okay, you might need order of 5,000 tests to cover all transitions for the L2. That number probably goes up to more in the 20,000 range for a multi-cache system. And that's just to get through each of the singleton transitions. Then you start saying, okay, I want to cross these things. I want to see that I've seen each agent be a master, each agent be an aggressor for a snoop, each agent being a victim for a snoop. So sky's the limit, right? This is why you end up running more and more of this test and run very high volume in post-silicon looking for problems. Another aspect I might throw in while I'm here, Mike, is that one of the things that are very interesting in running on post-silicon platforms is that you're no longer looking for, in many cases, you're no longer looking for logic bugs. You're starting to see lots of electrical effects in these big designs where you might get tiny power glitches that cause you to lose certain bytes of memory in your cache, or you might get issues going across your serial interface. Right? We do PCI-like interfaces across chips, and under load, sometimes we're seeing them fail. So there's many good reasons to run heavy tests in post-silicon that don't even have to do with the concern that my verification wasn't good enough. But long story short, Mike, yeah, we don't know how many tests I needed.
Okay, that's a short answer. And how do you make these tests self-checking?
That's an important question. The transition tables will give you enough information to be able to do both so-called data checking. Does my cache line have the right data in it? And state checking. Is my cache in the right state, modified, exclusive, invalid? As well as, hey, if I send this transaction to this state, to the cache in this state, then it should send out this loop to the next guy. So the transition table has enough information to check all of that. So we drive the transaction, we check to see that the right state change happened, the right transaction output transaction happened. That works at the unit level, and that works at the subsystem level. Once you go to a software-driven environment, the CPUs tend to be too far away from the caches to be able to get the control and observability that we want. So at that point, we stop trying to do the state checking and the transaction checking. What we're doing instead is making sure that data check is correct. So whenever we read a location, we check its value to make sure it has the value we think it should have.
Okay, thanks, Adnan. Any questions?
Hello, Cambridge. Do you have any questions, please?
I guess my question was, how does the test generation time compare with the test execution time when you're running in hardware acceleration or silicon?
This is an important question. I caught the question. The test generation time for us is a little bit faster than the compile time, so it's the order of the compile time. And then there's generation, there's compile, there's download, right? So this is an issue. In emulation, it tends not to be an issue. The tests run a good deal longer than it takes to generate and run. In post-silicon, this is definitely an issue, and it requires regression systems where we have many Linux systems generating tests offline, so we can keep the chip busy 100% of the time. But these solutions do exist. It's silicon. Of course, again, everything's subject to what you ask for. You can put loops in these tests and make them crazy long, and you can keep your silicon busy for a long time as well. But nonetheless, it's an offline generator, so it does have the weakness that it has the strength that it can be very smart about the tests it generates. It has the weakness that we have to compile and download the test.
Okay.
Thank you, Brian. Grenoble, do we have any questions from Grenoble, please?
Yes, we have one question. Yes, do you hear me?
Yes, we can. Thank you. Would you like to go ahead?
Thanks. This is Laurent Martin-Boré from ST Microelectronics. I have one question, Adnan.
Hello, Laurent.
Hi, Adnan. Actually, my question is related to the reuse of tests from one level to another, or from one platform to another.
Yes, sir.
Are there some specific packaging that you do to easily reuse the test from, for example, IP level to SOC level?
Specific packaging. I think the trick over here that, as far as I know, all of us who are working on this Accelera standards group agree on, right? We haven't agreed on how to do it, but I think the general approach is let's create the model itself at a high enough level of abstraction that tools can go off and map them to the right platform. So in our case, for example, once we have the transition tables, we turn them into some graph-based model. But then the tool has a bunch of switches that let you control how it generates a test. And what we're doing is we are picking the right configuration for the platform aware test generator such that it'll generate the right test for your platform without modifying the platform. So in the UVM environment, for example, we might drive all of the UVM sequences on each of the VIPs, whereas in simulation we might generate a C program where we use lots of backdoor access for checking, and in post-silicon, instead of doing backdoor accesses, we might compute checksum on the data instead for checking. So it's not so much a packaging problem as an abstraction problem.
Yeah, I understand the point, Adnan. I understand that your tool is able to cope with such, let's say, parameters. But my question is more global. When you go from one platform to another, you go from one environment to another.
Yes, sir.
But you want to get all the information related to the tests you want to perform from, I don't know, from a SOC level simulation to post-silicon, for example.
Yes.
And you need to gather all this information from the SOC environment to the post-silicon environment. So you need to do some packaging at some point. My question is actually not only for you, Adnan, but also probably for Larry and also for Mentor. In the portable stimulus work group, is there something tackling this packaging point?
The packaging is at your point of what is the configuration of my SOC, how many CPUs, how many memories, this kind of thing? Or are you thinking about the coverage kind of information? Where is your mind at?
Actually, what I mean is that we need to port the test from one environment to another, and we need to do some things to do that. I mean, we need to gather all the needed information to be able to run the test on one platform or on another one.
Give me an example of what you're thinking of. Actually, I'm sure all three presenters want to know what you're talking about. So give us an example of the kind of thing you have in mind.
This is more or less part of things that you said in your talk. When you write C code that is to be run in the simulation context, probably it's not the exact same C code that will run in the post-silicon environment.
This
right?
is correct. Yes.
So in the code written, maybe there are some defines or whatever, I don't know, and these have to be controlled at some point to be used in the right way when you go at post-silicon level.
Yes, sir. So the tool absolutely must be configured for the platform.
You take care of that, I guess, when using your tool. But what I mean,
yes,
what I mean is to gather all these pieces of information for all the tests, maybe not only your test, but all the tests which are present at one level of hierarchy, and to port them at the post-silicon level. There is some packaging work to be done. And this is my question, actually. Is this packaging work is addressed by the portable stimulus work group?
I am guessing that you're talking about packaging this information to hand off to the next team. Is this the point of your question, that maybe the simulation team ran a bunch of tests and now they wish to hand them off to the emulation team saying, here's what I did? Might that be what you're thinking?
Hello, I'm very sorry. It seems that we have some audio issues with Grenoble. It's coming in and out on the webinar, so my apologies for that. What we can do, Grenoble, if Massimo can take the details of that, of the person asking the question, we can deal with it at sort of post-event. That's possibly the best way to go about it. We don't have any more questions online, so that just leaves us to thank Adnan and Hamid for his presentation today. So very much appreciate it.